Hi guys, I know this is frightening seeing me this close. Did you guys have a good weekend? Or at least reasonably good? I think we always have less people in here, so we're just gonna do our best. We're just gonna do our best. Stuart, how are you doing?
Good.
We're getting through. We're getting through. Muddling through, I hear. You guys saw the video? I mean, it seems like once it quits buffering and like starts coming down at full speed, that it is at least somewhat reasonable. Somebody had an idea last time to stop and take pictures of the board, and I'm going to do that at various times, and that'll be on our canvas. Okay, so in case you can't read the board at certain points in time, I want to make sure that you guys have at least a couple photos of that. I apologize that, I don't know. I may still have to try to find a room where we can be, where we can all be together all the time. But today it'll be pretty bored, so you'll just be like, oh, okay, Dr. Well, I don't mind actually watching it from my room when it's raining. I gotta muddle through the rain to get here. Hopefully you guys are nice and dry in video land. I'm gonna try to stay away as much as possible. Okay, what did we learn last time? We learned about similar triangles. How about in the video, what did we learn last time?
Distance.
Distance. Okay, we took our idea of distance. Sorry, I know I'm not in the video. I'm back. Okay, how about that for athleticism? The distance between two points, but in three-dimensional space, okay? So if I've got, instead of two coordinate axes in three-dimensional space, we need three. That's one person. So I draw, you draw, so I draw this and you draw that, okay? So we've got our three coordinate axes. This one's coming out of the wall at you. This one's coming out of the wall. I forgot my vectors today, so we'll have to kind of like struggle with this. I want you to label those. Without looking at your notes, label those. Okay, you're gonna help me out. Stuart, what's this one? X. Behind Stuart, Zach, what's this one? Z. And behind Zach is? Luke, what's this one? Y. Okay, so we have this, and then what we're gonna do is we're gonna pick two arbitrary points. We're gonna pick two arbitrary points in our three-dimensional space. So you do that. You draw two little points in your three-dimensional space. Okay, and label them if you can. Label them. You just think about doing the best you can. Label them. And you at home, you should be doing the same thing. You should be, if I draw, you draw. If I draw, you draw. So pick 2 points in your three-dimensional space. You guys have learned to stay out of my way here in the middle. Like. Okay, now cheat. Show somebody else what your points are. Don't just hold them up so that don't breathe on them. But cheat, look around. See if you've got anything that anybody else has. So there's mine. Here's my 2. I'm pretending they're out here in this first octet where everybody's positive. Let's call point 1. What did you guys write here? What did you guys write here? Did you write anything there? Anyone? You called it P1? And what'd you call this one? Nothing? P2? Did anybody give them coordinates? Anyone? Did you give them coordinates? What would the coordinates, what might you call the coordinates at this point? It's arbitrary. What would you call it? And at home, what did you call it?
2, -2, 2.
Oh, yeah, I guess we could do, yeah, I was more thinking arbitrary, but I like that, 2, -2, that would be, let's just call it x1, y1, z1, and then you guys fill in the other point, you fill in the other point. What's your name?
Gordon.
Gordon, so this would include your point, this would include your point. Okay, now, hopefully everybody has a what here? I'm not even looking at your notes, tell me what to write down.
X2.
That's good. Y2 and, okay, now at home and at your seats, write down a formula that represents the distance between those two. Write down a formula, what you got in your gray matter, without looking at your notes. Write down a formula that represents the distance between those 2 points. Okay, sorry, what's your name back here again?
Mason.
Mason, what do you got for me?
The square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared.
Okay, did anybody else have that? Did anybody else have that? Okay, guys, you need to have flashcards. You need to have flashcards. Okay, do not make all 150 flashcards that we have so far. This is your first flashcard. This is your first flashcard. So on that sheet that I handed out, I want you now, not now, but for homework, make that flashcard. So you have the distance between 2 points, x1, y1, z1, x2, y2, z2, and there's your distance formula, and there's your distance formula. Now, is somebody at a big advantage if they have all their flashcards memorized heading into the first quest, for that first quest, and you don't? Would they have an advantage? Even if you're smarter and understand the material better, might they have an advantage? You know, so yeah, so I mean, we can't memorize this class, but we can sure as heck make use of memorization. Okay, now draw an XYZ coordinate system. Draw an XYZ coordinate system, and you guys should be drawing at home too. They're working, you're working. And I want you to mark on that the point 3, 4, 6. Mark the point 3, 4, 6 as best you can in your 3-dimensional coordinate system. Okay, show somebody else your art. Show somebody else your art. And I don't know how you're doing this in the video, but you should be showing somebody else your art. Okay, so you guys help me out. This would be, we would go out, let me get out of your way. We would go out 3 along the x-axis. Then we go out 4 along the y-axis. So we're kind of running parallel here. And we're going to run 4 along this, and then from this point we're going to go straight up, but I'm going to go visually a little past higher, so that's kind of like a line going back in there, and we go up 7.
6.
No, thanks. Sorry, 6. I need you guys. Okay. So the coordinates of this point, in 3-dimensional space is 3, 4, 6. Okay, now S is going to be, you're like, oh crap, it's A. Oh crap, it's A. Oh crap, it's A. Set. So S is the collection of all the points in 3-dimensional space that are, it's the set of all the points out here in 3-dimensional space whose, sorry, that are, I guess proper English, that are 5 units from 3, 4, 6. So imagine I'm out here, you said you go out, if I'm starting here, I'm at the origin, I would go out the x-axis how far? I'd go out the x-axis how far? 3, and then Zach, what do I do then? I'm over here at 3, and then what do I do? Go out along the something parallel, and then I go up 6, and I want all the points, all the points that are 5 units away from this point. So if I'm thinking about that, can you visualize what that would look like? So if I go 5 back that way, just straight back that way, would that be a point? Would that be a point that's in S? And if I went 5 units straight up, would that be a point that's in S? And if I went 5 units straight down and was just 1 unit off the floor, would that be a point? If I go out 5 units in every single direction, what are you going to get, guys? What are you going to get? A sphere. You're going to get a sphere. So this set S is really describing a sphere. Now, does this seem like the best way to write down a sphere? Would you want to write this down every single time that we had to talk about a sphere? So let's try to come up with a better way to describe S. Let's try to come up with a better way to describe S. So you want all the points that are 5 units away from that point there. Now I'm going to try to do this. You guys said a sphere. So I probably drew it too big. But maybe something like that. There's our sphere, and we know that to be a point on the sphere. So here I started at the center, and here's a point that's on the sphere. Let's just make it arbitrary. Because I want a formula. Let's just call it XYZ. It can be any point on the sphere. Well, what do I know about XYZ in 3, 4, 6? This arbitrary point on the sphere in 3, 4, 6. What do I know about that?
It's the center.
It's the center, but what else do I know about it? This point that's on the front of the sphere here, it's out here, and it's going back to the center that's there. What do you know? It's 5 units. It's 5 units. So it's really a sphere of radius 5. Now, can you come up with a relationship that might be better than these words? So try it. Can you come up with a relationship that might be better than those words? I'm going to try to keep you guys busy. And this is what stinks when you're not in my room and I'm teaching just to a camera, which I fear may happen. I had more time. Wish I had you guys 7 days a week, 8 hours a day. We would have so much fun together. You're like, no, we wouldn't, Dr. Warren. We could go to D Hall together. We'd all catch the coronavirus together. What do you guys think? Help me out. I mean, I don't have that much time. So what do you guys think? Any ideas? I could write an equation of a sphere, and that's kind of what I want to get at. The equation of a sphere. Well, what do I know? This point is this point on the sphere? Is this point on the sphere? And this point is the center of the sphere. Oh, sorry. This will be taking a station identification to take a picture. What do you know about the distance between these 2 points? It's 5. Do you think you could use this formula? Do you think you could use this formula to help you out? Do you think you could use the distance formula? This is an arbitrary point that's on the sphere, and you just told me the distance is 5. So plug locations, plug things into that formula. Plug things, and you at home plug things into that formula too. So plug the quantities of interest. That's a kind of boring term. Plug the quantities of interest into the formula. I just still want to get out amongst you. I feel like a prowling lion, you know, and I'm like being kept from my prey. There's this fence between us called coronavirus. And I can't see. I want to get out there and see what you guys are writing down. Anyone? We'll do Ferris Bueller's Day Off. Anyone? What do you have? Anyone? 5 equals, okay. Anybody have that? And what do you have on the other side of equals? Square root. And then what?
X minus 3 squared.
Josh, it is Josh, right? X minus 3 squared, because there's that's kind of like the x2. This is kind of like the x1. Go ahead, Josh.
Y minus 4 squared.
I'll get out of the way.
Z minus 6 squared.
Z minus 6 squared. So like that. Did anybody else get that? Now, could you make this a little bit cleaner? Like if we're thinking about coming up with a formula, what might you do? And that's what we're trying to do. We're kind of coming up with our second flashcard. What would you do to make this formula a little bit cleaner? Square both sides, and if you squared both sides, you'd have 25 is equal to x minus 3 squared, just what Josh was telling us. Does this make sense? And so another way of writing this would be like this. S is you read it to me, and you read it at home. S equals the set of all the points x, y, z, such that 25 that statement is true. So it should make that statement true. So if you're a computer scientist, this returns a true. But most of the time, guys, we don't write the set. We just write, oh, this is the equation of the sphere of radius 5, whose center is 3, 4, 6. Okay, so now let's just jump this up to a general flashcard. And this is where I would have you jump up. And jump up in the air just to wake up. So I can't do that, so just look at somebody and say, wake up. Wake up. So here's going to be our formula. We're going to have a point ABC. These are numbers. We're going to have a point ABC. We want the formula to work for any sphere in three-dimensional space. And the radius is going to be R. That's going to be an arbitrary point. On the sphere. Okay, you write down what you think the flashcard is going to be. What's the equation of that sphere? Okay, please, I'm believing everybody's got it right. So here in the yellow, what's your name? Yeah, Kate? So,
Ava.
Ava? Yeah, Ava, what do you got for me?
R equals the square root of x minus a squared plus y minus b squared
Love where that's going, love where that's going. If you wanted to make it a little bit sweeter, just a little bit cleaner, Ava, what would you do? What would you do? What might you do?
You would change it to R squared,
Change it to R squared and then,
get rid of the rest.
perfect. And guys, this is in fact, this is the flashcard that I want you for the equation of the sphere. It's equation of a sphere of center, equation of a sphere with center, equation of a sphere with center, I'll keep hitting the ball. Equation of the sphere with center ABC, point ABC and a radius R. Okay, so now try this at your seats and try this at home. Here's the center, guys. Here's the center of the circle. X is -2, Y is -5, and Z is 12. The center is -2, -5, 12, and the radius is 10. Write down the equation of that sphere. Okay, cheat, look around, see if you got the same thing that others have. I mean, at least hold it up so other people can see it. And I'll look at yours at home. You guys are doing great. You guys are doing awesome. I can't believe I'm teaching you through this. Okay, what do you have right here? What's your name?
Wait,
Wade?
Yep.
Wade, what do you got for me?
100 equals, parenthesis x plus 2 squared plus y plus 5 squared plus z minus 4 squared.
Perfect. Now again, I'm sorry guys at home. I'm sorry, this is what my board looks like. Okay, so I'm gonna write down, we're gonna play this game, and you're gonna tell me as quickly as you can, what's the center, and what's the radius? So that's gonna represent a what? If I take the collection of all x, y, z points that satisfy this is immediately gonna be, bam, I hit that, and you're gonna say, Dr. One, that's gonna be a sphere of center -7, -9, -8, -9, the radius is 5. How many people believe that they kind of understand this sphere thing? Okay, one last question, then we're gonna stop the sphere. Imagine that you've got this point in three-dimensional space, and I'll just say, suppose just I'm out 3, 4, 5. I'm not really being very creative. I'd come down the x-axis, I'd come down the x-axis, I'd come down the x-axis, and I'd go over the y-axis, over on the y-axis, 4, and then to hit the point, I'd go up 5. Okay, and I want you kind of find the equation of the sphere, that would, whose radius would just kiss this back wall back here. You've got this plane, which is, this would be which axis? This would be which axis? Y, Z, X. What would the equation of the sphere be where the back of it just touched in one single point the YZ plane? Or the plane x equals 0, or the plane x equals 0, okay? If x is 0 and y and z are allowed to do whatever they want, Dr. One, don't yell at me. I've got to give you guys the power to focus. I give you the power to focus. I give you the power to focus. Okay, I want the equation of the sphere whose center is, see, you got the power. And whose back part of that sphere is just going to kiss this plane back here. Try that, see if you can come up with that. See if you can come up with the equation of the sphere, where the back edge would just kiss that plane, x equals 0, or the YZ plane. And I'll take off my desk. Oh. Can I really do this when I'm 70? That's the real question. And this is when you'd be in groups. This is when you'd be in groups. I have you guys. What do you guys have for me? What do you have for me? Anyone? I mean, I don't have time. What do you guys have for me? Anyone? Does anybody have?
X minus 3 squared plus y minus 4 squared plus 3 minus 5 squared. And so equal to 3 squared.
Equal to
I'm not sure.
3 squared?
Yeah.
Anybody else have that? Anybody else have that?
I don't know if that's right, that part.
What's your name?
Rachel.
Rachel. Yeah, nice job, Rachel. Let's give it up for Rachel. Come on, she can win out. She knows this. Okay, so Rachel, explain to us your thinking.
Since it would be on the YZ plane, it would be something at X. The plane would be at something at X, so you take the X coordinate from the center.
That's exactly right. Perfect. So if I wanted to go, the easiest radius to grab would be the one that started here at the center and went straight back and kissed that wall back there. Well, how long would that be? And I'm so sorry, I am so attention deficit. What's your name again?
Rachel.
Rachel said, well, Dr. Warren, you came out the x-axis how far? 3. So this would be the same distance. That would be this plane that contains the center. That wall would be 3 units away from that wall. And so I think that's where Rachel was going. So do you think Rachel's right? Do you think Rachel's right? Yeah, so what if I said, okay, no, I really wanted to kiss the y equals 0 plane. I really wanted to kiss this plane over here. What's the only thing that's going to change, guys? What's the only thing that's going to change? Instead of 3 squared, we're going to have a 4 squared. And what if I went just the z equals 0 plane? What would the radius be? 5 squared. That would be the equation of the plane. Sorry, the equation not of the plane. I'm a moron. Equation of the sphere. Thanks, Stuart. Okay. Time this class in. 11. Take out your phones. Take out anything you need to tell time. What time is it?
10:14.
10:14. Oh, I shouldn't do this, but I'm going to. I should just start vectors. But there's one other formula I want you guys to have. See, my undergraduate major was not math. You're like, Dr. Warren, I can kind of tell. My undergraduate major was art. I was an art major in undergrad. I know, it's unheard of, okay? No, I was an art major in undergrad, and then I got my math degree. And like I said before, the only school that would take a chance on me was JMU, okay? Proud Duke. Are we perfect? No. Are we better than all the rest? Yes. Sorry, UVA. Not even a candle. Arrogant. No, sorry. We're videoing this. Okay, sorry. Go. Oh, that's great. What the? That's school pride. I just said we're the very best, and that's what you guys have for me. Sorry, we won't go again. I don't want to spread the virus. Okay. As an art major, when I was thinking about Calc 3 and learning it, I was like, wait a second. This can describe things in 3-dimensional space. I could probably do some pretty cool design stuff with this. And so one of the projects the high school came to me for, they wanted to put together a Statue of Liberty crown that they could use at their band competitions. But guess this, they wanted the crown to be 30 feet in each direction. And it needed to go into a truck, and they wanted it to look like the Statue of Liberty. You're like, Doug, want to use an art major, seriously? They wanted to have that Statue of Liberty look, and then they wanted to have the things coming off in all directions, but this needed to lay flat on this plane. And it needed to be built out of plywood. It needed to be built out of plywood. And there's amazing construction people in this town. And I've worked with some of the very best. I mean, they're just incredibly creative people. But to get a piece of plywood to lay flat on this, where you've got supports coming up at all these different things, to build it a little bit at a time was going to be impossible. So I needed to figure out all the different angles in each of these pieces of wood, all the different angles that would support, because all of these were like the Statue of Liberty crown. I needed to know all the angles, they needed to support them, and then we needed to put a piece of plywood flat on that. I gave them all the miter angles. When they went, cut it, and when the piece of plywood just sat right on the top, they were looking at me like I was some heavenly being. You know, they were just like, they'd never seen anything like it. They made these pitched roofs before, but they never had, like, let's make a Statue of Liberty crown, and let's lay it all out ahead of time. And it was all Calc 3. It was all Calc 3. Every single part of it is Calc 3. So in some ways, when I'm thinking about you guys, I'm always thinking, oh, they could use this to build. They could use that to build. And I know I should be teaching vectors. I'm like, no, let's talk about distance formula. Might that be useful if you're building something? I mean, think about a CAD program. Okay, so now another useful formula in three-dimensional space is the midpoint. Does that make sense? That might be useful. I mean, even like if you're thinking about like just simple rod, you have this rod. If it's uniform density and you want to support it in one location, you want to hit it center of mass. So you want to put something right there in the center of the mass. So that's just in three-dimensional space. That's just a simple midpoint problem. So my question is, you've got these 2 points in three-dimensional space. Again, we'll go back to P1, P2. I'm not going to name them. This we'll call X1, Y1, Z1, and this we'll call X2, Y2, Z2. And what I want to know is what's that midpoint right there in three-dimensional space. So I'm coming out X1, I'm going over, I'm coming out the X-axis X1, I'm going over. I'm coming out the axis X1, I'm going over. Okay, and I'm coming up. I've got another point where I've gone a little bit further, gone out, gone over, gone up. And then I want to find the what on the line segment between those two, the midpoint. You're like, Dr. Warren, that sounds awfully. Does that sound like a fun thing to do? Does that sound like an easy thing to do? Like, for example, let's just pick some points. Suppose this is, I'm not 2, 4, 7. And this is 10, 12, 15. I want to know the exact 3 coordinates of the midpoint along that, we'll just think of it as a beam. I want to support it with one column going down. Where it's perfectly balanced. That's taking the weight of the load there in the center. Does this sound like an important problem? I mean, like, does it mean like you're thinking about it? So the question is, if it's math, sorry, if it's engineering, it's usually memorize, sorry. Let's never show anybody this. It's physics, wave hands, and then memorize. Sorry, physicists. They're always right. The physicists are always right. That's the thing that annoys me. Their hand waving is always correct. Their instincts are like incredible. But with mathematicians, it's always prove it. Say that. Prove it. What, you know the Nike slogan, just do it. In math, it's just prove it. Yeah, I want to get a big swoosh. Just prove it. So if we're thinking about this, how would we do that? And so I'm not gonna take too much of a journey, and I'm not gonna knock it out for you, because it's not really, super vital to the course. It's important, but it's not super vital. Let's just go back to one dimension. If we can't understand midpoint in one dimension, are we totally screwed in 3 dimensions?
Yes.
Okay, so I've got these 2 points. I just need one coordinate in a one-dimensional thing. I've got these 2 points on the number line. I only need one axis, the x-axis, one number line. And I've got, start at 0, I go over x1, that's 1 point. Dr. Warren, I wouldn't focus at all. And I can tell you guys are zoning at home too. The moment my voice starts getting hoarse, I know I'm just beating you. I just know I'm beating you. I start at 0 and I go over. Or I could start at 0 and I could go over. And I'd like to find the midpoint between them. I'd like to say, how far do you have to go over to hit this midpoint? Does anybody remember the formula from high school? Great, your teachers are so happy. Anybody remember the midpoint formula from high school?
Just x1 plus x2 over 2.
It is in fact x1 plus x2 over 2. What's your name?
Gordon.
Gordon, yeah, Gordon, your teachers are happy. All the rest of you are like, Gordon, thanks for stepping up for us, man. Thanks for stepping up. Okay, so let's try to understand why that is. Let's try to understand why that is. Well, I could start at x1, but is that enough to get to the midpoint? One more time, that's why I'm gonna focus. I could go over x1, but is that enough to get to the midpoint? No, so let's at least start at x1. How much more do I need to add on to get to the midpoint? How much more do you need to add on to get to the midpoint? Half of this distance. Now, we were talking about distance the very first day of class. How do we find the distance between 2 points on a number line? Subtract. So this distance here would be what? This distance here would be what? Okay, yeah, I mean, we want m. Can you represent it in terms of these guys? Can you represent it in terms of these guys? Well, we know this plus this, you guys are right. I mean, you guys are right. But I need something else. What's the distance between these two? x2 minus x1. What's half that?
x2 minus x1
Perfect. So you're like, damn it, Dr. Warren, I didn't think it would be that easy. So would this not be x2 minus x1 over 2? Wouldn't that be that distance there? So let's add that on. Let's add that on to here. So I go over m, and then I add on x2 minus x1 over 2. Would that get me to m? Would that get me to m? So now you're like, Dr. Warren, how can I do this? Well, you're gonna make your high school teachers proud. You got a fraction plus this. What are you gonna do? What are you gonna do to combine them? What are you gonna do? Common denominator. So what would I need to do with this guy? What would I need to do with this guy? This is calc 3.
Multiply by 2.
Multiply by 2. Now could you add them? Now could you add them? And if you do that, you've got 2 of these guys, a minus 1 of those. What are you left with? What are you left with? What are you left with? You're left with 1, which gives us our formula right there. Which is our formula right there. So like Dr. Warren, that gets us a pretty far away from where we were at. We were living in 3-dimensional space. So let's jump up. Let's jump up to 2 dimensions. Let's jump up to 2 dimensions. This would be the point. I'm gonna let you guys, this would be the point, this would be the point, this would be the point. See, I'm making a face and nobody sees it. Pretend like you see me. Do it with my eyes. This would be the point. But we're in 2 dimensions. We're in 2 dimensions. So it'd be x1, y1, and this would be the point x2, y2. And even though we don't think about it this way, and I know you're not even listening, I could say whatever I wanted there. Chew bubble gum, you would have heard the same thing. Chew bubble gum, 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 chew bubble. Taking this. Just like what we were over here, you start at the origin. But now you go over x1, you go up y1, and to reach this point, you go over x2, and you go up y2. And now I've just got this thing in the plane. I've got this thing in the plane, which is far less fun than our three-dimensional thing running around there. But again, what do I want to find? What do I want to find in here? The midpoint. I want to be able to tell somebody, you start at the origin, you go over this way, and you go up that way. And I'd like to try to figure out how that is. You know, like with Dr. Warren, I kind of like what we were doing here. I kind of like what we were doing there. But this seems a lot harder. Well, things that seem harder in Calc 3 often require similar triangles or Pythagorean theorem. So let's try to find some similar triangles. So you try to find some similar triangles. And you at home try to find some. Can you see, like that one, there's no triangles. See if you can maybe draw some triangles. Gosh, it's 10:27. What time is class then? Okay. If you guys at home are not working right now, I'm gonna be really angry. You're sitting there with some kind of drink in your hands. Well, these guys are working hard. I'm gonna be really angry at you. Does anybody have a triangle? Does anybody have a triangle? Does anybody draw a triangle? So tell me what you did. Just hold up your art. Hold up your art. Hold up your art. Show me your art. Yeah. Show me your art. Yeah. I'm seeing lots of good art. Your art is beautiful. Look at me, guys. This is not an art class. I'm not judging you by your art ability, okay? So it's just the rough ideas. So if you think about it, if I do this and that, would that be a right triangle? Would that be a right triangle? Anybody get that triangle? Did anybody get that triangle? And then you could do it a couple of different ways. But I'd probably draw that one just because to me it's a little easier to see. To you it's maybe not, but I'm gonna put that one there too. Are these three lines parallel? Well, not the way you drew it, Dr. Warren. Are these three lines parallel? Yeah, so this angle would be the same as, this angle would be the same as that angle, and they both share that angle. If this is going to be the midpoint, and for lack of anything better, I'm just gonna draw it as smiley face. This distance from here to here is going to be smiley face. That distance from there to there is going to be smiley face. Then what would the distance from here to here be? Let me get out of the way. If this distance from here to here is smiley face, what would the distance from here to here be? Smiley face. Now, can somebody give me an expression that represents that distance right there? Could somebody come up with an expression in terms of what we have in play? You're like, well, Dr. Warren, no. So let's give this guy some coordinates. If it's the midpoint, what might you call it? I mean, you can call it whatever you want. Don't give me a number. Let's call it 5-7, Dr. Warren. What? What might you call it? I like that, Stuart M1, M2. Now in terms, oh, wait, Josh, is that you speaking first? No, Josh, I like that. It's exactly what I wanted. I didn't pay you before class, right? Tell them. Did I pay you to say that? Okay, good. We're on the same language, Josh. I hope it works on the quests. Okay, so now we're here. M1, M2. Could somebody give me an expression that represents that distance, and what would it be?
Y2 minus M2.
Would it be Y2 minus M2? I mean, if you're thinking about, would this distance be, if this would be M2 here, this would be M2. Is this distance the same as that distance? One more time, Dr. Warren. Is this distance the same as this distance? And this would be y2 minus m2. Now how about this distance? How about that distance? One more time, Dr. One. This distance, what would this distance be? What would that distance be? What would that distance be?
X2.
How about this distance here? What would that distance there be? What would that distance there be, guys? That bottom, this bottom thing, what would that be? X2 minus M1. I probably didn't do that real great, but that's, how about this distance? And you're like, Dr. One, which one? The distance from there to there. The distance from here to here. What would that distance be? The distance from there to there. What would that be? Y2 minus Y1. Let's do some English here. Okay, so take a picture of the board. Breathing. Okay. Is this triangle similar to this triangle? One more time. Is this little triangle similar to this big triangle? Or sound like a sneaking walrus. Are all the angles the same? Some of you are still sleeping. You're making walrus noises in your sleep. Are all the angles the same? So would they be similar triangles? What do we know about similar triangles? What's proportional?
A over the side.
Yeah, so are you ready to like say this? Corresponding sides, say that. That wasn't everybody, say that. Of similar triangles are proportional. So say that to your child. Use your finger out. Say it. Corresponding sides of similar triangles are proportional. Could you imagine if I was your father? Could you imagine that? Okay, so let's talk about these triangles here. So I would know that y2 minus y1, this long vertical side here, y2 minus y1 over m2 minus y2, this thing right here, would be proportional to, let's go to the hypotenuse, would be proportional to what? Would be proportional to what? I know that this side over that side, this side over that side, would be proportional to this side over, this side over, this side, I'll keep going, this side over that side. Does that make sense? Does that make sense? One more time, Dr. Warren. This side over this side would be proportional to this side over that side. Does that make sense? We have the big one on top. We have the big one on top. So I would have a smiley face plus a, I'd have a smiley face plus a, I'd have a smiley face plus a smiley face over a smiley face. I would have a smiley face plus a smiley face over a smiley face. Now, what is a smiley face plus a smiley face? I'm smiling and you can't even see it. A smiley face plus a smiley face, don't say a smiley face. How many smiley faces do I have? Two smiley faces. What happens with the smiley faces? They cancel. No, actually, probably you can't even focus now because I've drawn on my mask. Okay, so I'd have 2 is equal to y2 minus y1 over m2 minus y2. Now let's solve for m2. Let's solve for m2. What would I need to do to try to solve for m2? What would you, go back to high school, what would you do? What would be your first move? You're gonna get m2 by itself, what would you do? What would you do? What would you do? What would you do?
I have a question.
Yep.
Do you mean y2 minus m2 for the smaller side?
Yeah, I do mean. No wonder you guys look confused. You're always right, just stop me and say, thank you. And it's on video. Bless you. What's your name again?
Gordon.
Gordon, I'll get it. Okay, all right. Now we're all on the same page. Somebody like, no, Dr. Warren, I'm zoning. I'm so out of shape. I'm so out of shape. How many people it's hard to listen for an hour and 15 minutes? Some of you guys are really good. I feel a kindred spirit back there with me. I feel a kindred spirit. Okay, now, if I wanted to get M2 all by itself, what would you do? If you wanted to get M2 all by itself, what would you do? Move it to the other side. And if you did that, you'd have y2 minus y1 equals 2 times y2 minus m2. Now all I'm gonna do is I'm gonna get this guy, I'm gonna take this 2, I'm gonna take this 2 and just bring it under here. And then what I'm gonna do is I'm gonna bring the m2, and I know that you're writing it, so you're not even. I'm gonna take the M2 over here. I'm gonna take the M2 over here. I'm gonna take this junk over there. I'm gonna take the M2 over here. I'm gonna take the M2 over here and take that junk over there. What would you get if you did that? What would you have? Help me out. There'll be one person.
M2,
Oh, thank you. Equals
Y2 minus.
Y2 minus. Okay, now, if I wanted to simplify that, I'd need to get a, if I wanted to simplify that, I'd need to get a, if I wanted to simplify that, I'd need to get a common denominator, put that 2 over 2. Now do the minusing right, and simplify it at your seats. Do that subtraction right, make sure you distribute it across that numerator. And when it simplifies, what do you guys get? When it simplifies, what do you guys get? What do you get that M2 is equal to? Y2 plus Y1 over 2. And you're like, what, Doc? Zach's like, hey, Dr. Warren, that's kind of interesting. If instead of working with the vertical sides, I worked with the horizontal sides, what do you guys think when the smoke cleared you would find M1 to be? I mean, if you just, what do you think you'd find? X2, doing this the exact same thing, X2 plus X1 over 2. I probably didn't set the similar triangles up in the easiest way, but we still got there. Now, I'm not going to derive it in 3 dimensions. I'll let you guys think about it. I'll put up a picture. But if there was any mercy, what do you think the midpoint would be in 3-dimensional space? How many coordinates would you need? 3. You're going to have to come out, go over there. What do you think it would be? What do you think it's going to be? If you had to guess. And I'll put up a picture showing you how it lays out. If you had to guess, what would you think it would be?
X1 plus X2 over 2.
X1 plus X1 over 2.
Y1 plus Y2 over 2.
And then plus. I mean, isn't that cool? I mean, I didn't derive it. I didn't do math. But isn't that sweet that midpoint formula from 1 dimension extends to 2 and extends to 3 and extends to higher dimensions? So here's a question, builders. I've got the beam up here. We said this point was sitting at in through our room. This point is sitting at 247. This point is sitting at 10, 12, 15. So how how long do we cut our 2x4 to support that thing? How long do we chop our 2x4? What's our column height to support that? Put a middle support there in that beam. How high would we put that? How high would we put it, guys? Now I'm making you think like engineers. I like formulas, Dr. Warren. Should this be a flashcard? Should this be a flashcard? Let's make that a flashcard and make that our midpoint formula. Well, guys, what do you think? How tall should that column be? It should in fact be 11. It should in fact be 11. You're like, how'd you get that, Dr. Warren? Well, it's really the z coordinate. Isn't it really the z coordinate of this? You would go over M1, go over M2, then up M3, and so it would be this guy, 7 plus 15 divided by 2. 7 plus 15 divided by 2. Does this seem useful at all? I mean, does this seem, I know it's hard, especially at, take a look at your clocks. 10:42. Okay. And we all have masks on. Okay. Look, guys, I understand the sterility. You're learning from me, and I drew on my mask. Okay? It's surreal enough in this classroom just with me, let alone me and masks, and only half of us. Okay. Gently, without breathing, stand up. Gently, without breathing, just put your hands over your head. Gently, without breathing, tap your head. Okay, that should do it. Sit back down. What's your name back here in the corner? Ed. One more time? Ed, yeah, Ed. Okay, Ed, I'm with you. I'm bringing you with me. We're not losing you. When I was in class, I was always like that antelope on those nature documentaries that like all the rest of the herd crosses the Crocodile Creek and the crocodile, but you'd always know that one that's wandering behind. They always show that one. You just know that one when it goes across. That was always me. No, I was the last little antelope across the Crocodile Creek. And then teacher after teacher did the crocodile death spin on my grave. Okay. I'm gonna have to edit this video. The Greeks pretty much laid out geometry for us, at least as we learned it in high school. Who did that? The Greeks. And guys, when you go back, anybody ever traveled abroad to Europe? Anybody been in Europe? And I haven't either. I want to go. But when I look at what the Greeks built, like the Acropolis, where I look at the Colosseum in Rome, and some of the aqueducts, is that some pretty amazing engineering? When you go back and look at antiquity, and you look at the engineering they were able to pull up, wasn't that pretty amazing stuff? And they kind of all did that with pretty much just that geometry from the Greeks. And then as we advanced, we needed more this thing called algebra to really come in. And Descartes, the Cartesian coordinate system, and then laid in a formalism for algebra. And that kind of held us, this geometry and this algebra kind of held us until the 1800s. I mean, we could do calculus, we could do Calc 1 and Calc 2, we didn't need new numbers, new ideas of what a number was. But then in the 1800s, things started getting far more complicated. There was this thing called electricity. I don't know if Benjamin Franklin actually discovered it with a kite. I don't know. But the idea that there's this thing called electricity, and then I really think like if you take copper wire, and you wrap it around something, and you put a current through it, what happens? If you take copper wire, okay, and you connect it to a battery, what happens? It creates, the electricity is kind of in the battery, it creates a magnetic field. It creates a magnetic field. And has that been useful to mankind? Yes. What happens if you wrap it the other way? It creates and put a battery on it, it creates a magnetic field. Now, do those magnetic fields have the exact same action on objects? One rotates it one direction, and yet if you just wrap it the other way, it creates a magnetic field that runs it the other direction. And I really think it was the idea of gravitational fields that led to the idea that the geometry from antiquity and really the algebra that came in the 1700s was not enough for the 1800s. And they needed to extend the idea of what a number was. And really, I think they were trying to, at least Grassmann in the 1800s, was trying to bring together geometry and algebra. He was trying to marry them together to have this thing called a geometric algebra. An algebra for geometry. They were suddenly having a need for that. And I think, the idea that you could let this thing, we'll call it a vector, because that's what it's going to be, that points perpendicular to that magnetic field. The fact that it has a direction and points, here's where the field is. It's pointing up like this, and yet if we wrap it the other way, we need to point that thing in the opposite direction. The idea that a line segment wasn't going to be enough. There was direction involved, and that was it. 2 points determine a line segment, but there's not a direction associated with that line segment, which you need for forces, I don't know how Maxwell got his equations, but those things are pretty sweet. There's very few things I've ever seen in physics that I think is actually right. They're kind of right. Wonderful instincts. They work really well under certain conditions. But Maxwell's equations for electricity are pretty much like gospel truth in my brain. And I think it was having to deal with these concepts in the late 1800s that they decided that they needed a better language. And that's where the idea of, sorry, get 10 minutes. And I got to get the definition of vectors on the board. But I want you to have a little bit of history. In the late 1700s and the early 1800s, they found that if they use numbers like this, and what kind of numbers are these? Does anybody know? What kind of numbers are these? Complex numbers. This is my imaginary unit, I squared equals -1. They found that they could talk about rotation in a plane by using complex numbers. That you could really think of this as a rotation operator that would rotate something around. In Euler's identity, e to the I theta, which is cosine theta plus I sine theta, was essentially the key to that. And so they could use complex numbers to talk about rotation in the plane. And then the idea was, how could you extend this to three-dimensional space? What could you do to extend this idea of using rotation in the complex numbers, the complex plane, to three-dimensional space? And I didn't realize until this summer that Euler actually started it. I always thought it was Hamilton in the mid-1800s. But it was really Euler who really started the idea of using what essentially became the quaternions, which is essentially what Hamilton coined as the quaternions. Hamilton for a long time, and mathematicians for a long time, thought they could get away, if you think of this as being the y-axis, they could get away, you got your real axis, your y-axis, they could get away with just one more axis. For a long time, they thought they could use 3 numbers to really talk about that rotation in 3-dimensional space. But then they couldn't. And it was really Hamilton walking across, I don't know how to say it, I'm not Irish. It's the Broom Bridge. To me, it looks like broom, so I think it's the Broom Bridge. But on the Broom Bridge in Ireland, there's actually a diagram carved on it in honor of Hamilton, where he's got this IJK. He's got this IJK, and he's got I squared equals -1, J squared equals -1, K squared is equal to -1, and I times J equals K. He's got that carved in there, but how many people recognize I, J, and K? I mean, like, anybody taken physics before? Think about I, J, K. I mean that it was really Hamilton who coined that. And he coined the term vector. But he had this thing called the quaternions, where his idea of a number would be like 2 plus 3i plus 4j plus 7k. He had a real part plus these 3 imaginary parts. And he could use these numbers to do rotations in 3-dimensional space, to talk about things like what would later be magnetic fields. You can use these things to really describe rotations very well. But people were not willing to accept multi-dimensional numbers at that time. That this would be like a 0-dimensional part, and this would be like a 1-dimensional part. They're like, no, you can't add a 0-dimensional part to a 1-dimensional part. It really took around 2000 for people to really start embracing the quaternions. And I think a lot of it was due to gaming. I think it was the gamers. You know what I mean? But if you're talking about storing information, like for satellites, you think about how cool a satellite is. This is magic to us, right? Instagram. Oh. No, I mean, but we don't think about like, okay, but there's a GPS in here and the satellite's up there doing things and pointing to us. We don't think about all the math that's there. But this is far better. But Gibbs said, this is too complicated. It's just too complicated. The quaternions are too much of a mess. There's this multi-dimensional part you're calling a vector, and there's this scalar part. So he took Hamilton's product. This would be like 2 quaternions. These are like two quaternions. So this would be like A would be equal to A1 plus A1I plus A2J plus A3K. He took this scalar part and this vector part, and he just said, we're just going to work with that. We're going to call that a vector. And he took this quaternion product, and he broke it into 2 pieces. One he called the dot product, and the other he called the cross product. And said, well, no, we're not doing your thing. We're not doing your thing. But guys, at the cost of division, it cost the operation of division. You can divide quaternions. It makes no sense to say A cross B and give this notation equals C and talk about dividing. Well, if A cross B is equal to C, then A is equal to C divided by, but in quaternions we have division. So it was a huge mistake. It was a huge, huge error. And physics, engineering is still paying for it. This is my own personal opinion. It was a huge mistake and they're still paying for it today. But every Calc 3 book talks about the dot product and cross product, talks about vectors in these distinct forms, and so we're going to do the same thing. But quaternions and even larger number systems They found out that vectors weren't enough with Einstein, so he came up with this idea of tensor notation. And that seemed a little complicated. They came up with matrices. But then we found, oh, we really need the tensors. But the tensors don't have any of the geometry in them. So we still need new number systems. We've got string theory now. So even tensors are too complicated. So they really don't contain the geometry. Okay. We're going to finish class with me just writing down a definition. And you guys are now, I'm giving you the power to scribe. What is your job? Scribe. You're going to scribe. I'm going to... Math is fun. Math is proof. If we're going to prove things in this class about vectors, we're going to have a hard definition of what a vector is, and that's what I'm giving you right now. Your job is just to scribe. And at home, your job is to scribe too. I better make sure I keep it consistent. This is our personal definition. This thing I'm going to call an ordered triple. We don't really need this intermediate step here, but I wanted it there. I'll just number these for you. When you finish that, you can leave. When you finish writing that down, we'll pick that up. We'll pick this up for you guys on video form we'll pick this up on video form on Wednesday, and I'll see you guys live again on Friday. What's due on Friday? WebAssign, our first WebAssign. Sorry, let me get out of your way. You guys are great. Thanks for playing with me. Well, okay, you need to play better. Next time we're going to play more, okay? You don't look real confident. guys rather have just a video of like a hover cam? Or would you rather have the video of me at the board? The board, is that better than like a hover cam, just seeing a hover cam? Okay, then I'll keep doing this. Sorry, is that? What's your name again?
Wait,
Wade and Chase?
so the,
Wade and Gordon. And Rachel and Addie. Ed.
so don't really worry about flashcards for the time being?
Just the ones I just the ones I did.
Okay.
Those are the ones I did a bunch of work.
No, you did,
But